We begin this lecture series on advanced operations research. We earlier had a lecture series on fundamentals of operations research, where we introduced the basic topics in operations research. The topics that we saw earlier were linear programming, transportation and assignment problems, dynamic programming and inventory. Now we will look at some additional topics in the advanced operations research course. Before we get into these topics, let us first try and define operations research and look at some areas where this field has applications. Operations research can be defined as a scientific approach to decision making, which seeks to determine how best to design and operate a system under conditions requiring the allocation of scarce resources. The most important thing in this definition is the allocation of scarce resources for effective decision making. Invariably, the resources are scarce and it is necessary to use these scarce resources efficiently so that the decision making is made possible. Operations research also provides a set of algorithms that acts as tools for effective problem solving and decision making. So, essentially it is a set of algorithms and techniques which are problem solving techniques in nature, which can be used in the decision making process. As a field, operations research has extensive applications in engineering, business and public systems. Right from solving smaller problems or smaller sized problems in the shop floor to large problems in public systems, operations research tools have found applications in these areas. These areas listed here, which are engineering, business and public systems, are only indicative and not exhaustive. Operations research also has applications in areas other than these. OR, as it is called, is used extensively by the manufacturing and service industries in their decision making. Now, how did this field of operations research start? When did it start? So, the origin of operations research can be traced to World War II, where the British military asked scientists to analyze military problems. So, what started off as an application of scientific method to military is now called operations research. Over the years, it is also called as management science, and it can be also defined as a scientific approach to decision making that seeks to determine how best to operate a system under conditions of allocating scarce resources. In the earlier course, which was titled Fundamentals of Operations Research, we looked at these 7 topics: linear programming formulations, linear programming solutions, largely concentrating on the simplex algorithm, beginning with the graphical method and the algebraic method, and then moving on to the simplex algorithm. Then we looked at duality and sensitivity analysis. Duality talks about the existence of a dual problem to a given linear programming problem. The given problem is called the primal and the new problem is called the dual. So, we looked at all aspects of duality, the duality theorems, the weak duality theorem, the optimality criterion theorem, the main duality theorem, complementary slackness theorem and conditions, and sensitivity analysis. We also looked at the transportation and assignment problems, which are essentially network problems, but these are problems that can be solved using specialized algorithms that come out of principles of linear programming. Then we looked at a completely new approach to solving problems, which is dynamic programming, which essentially exploited the state characteristics of the problem. So, any problem to which stage wise decision making is possible, where decision making at a stage can be related to the best decision in the earlier stage, one could use dynamic programming to solve. Towards the end of the earlier course, we saw some deterministic inventory models which talk about applications of OR techniques to solving problems in inventory and materials management. Now, in this lecture series, which is called Advanced Operations Research, we are going to see a variety of topics. We begin with what is called extensions to linear programming. We are going to see all these topics, revised simplex algorithm to make the simplex faster than the version that we saw in the earlier course, how to adapt the simplex algorithm for bounded variables linear programming problem, which means if the linear programming problem has bounds on the variables, can we adapt the simplex method to solve the bounds instead of treating each bound explicitly as a constraint. Then we will look at column generation and cutting stock problems, which is one of the applications where we are going to apply these OR tools, particularly a form of linear programming to optimize the cutting stock patterns. Then we will look at the decomposition algorithm, where a large linear programming problem can be decomposed into smaller problems, and by solving the smaller problems individually and by linking the solutions, we can find the solution to the larger problem quickly. After that, we will look at the primal dual algorithm, which is essentially a kind of a dual algorithm where the dual feasibility is maintained, and when the primal becomes feasible, it becomes optimal. In the earlier course, we have seen some aspect of the primal dual algorithm. The Hungarian algorithm, which is used to solve the assignment problem, is an example of the primal dual algorithm. Then we start looking at the goodness of the simplex algorithm. How good is the simplex algorithm to solve a linear programming problem? What is its complexity? What kind of computing times it will take if the problem size increases, and so on. We will also look at goal programming, which is a way by which we address multiple objectives in linear programming. The standard linear programming problem has only one objective function, which is linear. If we have more than one objective function, how do we solve such linear programming problems? Do we convert them into a single objective and solve it using the simplex algorithm, or do we solve each objective one after another? Do we rank them? So, all these questions are addressed in goal programming, and towards the end of this module called extensions to linear programming, we will look at some aspects of polynomial algorithms for linear programming. We require algorithms that run in polynomial time, so that large sized problems can be solved effectively. Now, we want to check whether the simplex algorithm has a polynomial time complexity, or what are the issues associated with polynomial algorithms for linear programming. Now, these are the topics that we will see in the first part, which is called linear programming extensions. Then we move to integer programming. Integer programming becomes important when the decision variables take integer values. In a linear programming problem, the decision variables take continuous values, whereas in integer programming, they can take integer values or they can take binary, which means they take either a 0 or a 1 value. We have already seen some aspects of this. The assignment problem can be seen as a 0-1 integer programming problem, even though it can be solved as a LP, and therefore it is solved as a LP. In this module, we will look at all these. We will look at formulations of integer programming problems. Many real life problems are formulated as integer programming problems. So, we will see some examples of formulations. We will then go on to solve 0-1 integer programming problems through an algorithm called the additive algorithm, which is an implicit enumeration algorithm. Then we will look at solving all integer problems, which means all the variables in the formulation are constrained or restricted to be integers. So, we will look at the Gomory's cutting plane algorithm, which is a very popular and a well known algorithm to solve integer programming. We will also look at branch and bound algorithm for integer programming, and we will also look at what are called all integer primal and dual algorithms. The all integer primal and dual algorithms use the integer property of the coefficients, and in all the iterations the coefficients remain as integers. So, in terms of computational simplicity, all integer primal and dual algorithms score over the Gomory's cutting plane algorithm, where you may have variables taking fractional values in the intermediate iterations. Though from a computational point of view, Gomory's cutting plane algorithm is preferred to all integer primal and dual algorithms. Now, this would complete the second module or second part of this course called advanced operations research. After that, we will look at what are called network problems. Network problems are typically 0-1 problems or integer programming problems, but have what is called a network structure. Now, because of this network structure, you can solve them as linear programming problems and yet get integer valued solutions. First examples of network problems are transportation and assignment problems that we have seen in the earlier course as part of linear programming. Now, all the network problems have something called the unimodularity property, which means that if the problem is of the form Ax equal to b, the constraint coefficient matrix is unimodular, which means that the LP solution will give integer values. Now, this property is being exploited to solve all these network problems: transportation, assignment, minimum spanning trees, shortest path problem, maximum flow problem, and minimum cost flow problem. Now, the unimodularity property, based on which the LP solution will be integer valued, is used to develop and derive special algorithms which are based on principles of linear programming, but are slightly different from simplex, and these algorithms are used to solve these problems. So, we will look at an algorithm or two for each one of these problems. After this, we will look at the travelling salesman problem, which is a very well known problem in the field of operations research. It is also a very widely researched problem, and is usually, it comes under the category of easy to state and difficult to solve problem. Problem is well known. Given a salesperson who has to visit n cities starting from his starting point, how does this person visit each city once and only once and comes back to the starting point, travelling minimum distance possible? This problem has a history, and this problem has been researched extensively over the last many years. Now, in the travelling salesman problem topic, we will look at all of these: how this problem is formulated as an OR problem, what are the algorithms, particularly branch and bound algorithms. So, we will be looking at more than one type of a branch and bound algorithm to solve this problem. We will also be looking at heuristics. Heuristic algorithms are algorithms that do not essentially guarantee the optimal solution, but they provide very good solutions very quickly. The advantage is in the fact that computationally the heuristics take very little time and also provide solutions which are quite close to the optimal solution. Travelling salesman problem is a minimization problem, because we try to minimize the total distance travelled, and the heuristic solutions always give a value which could be the optimum or higher than the optimum. So, they act as upper bounds to the optimum solution to a minimization problem. We will also see some aspects of analysis of heuristics, how good the heuristic is, what is the worst case performance of the heuristic. So, we will look at those aspects by considering two very well known heuristics to the TSP, which is called twice around the tree heuristic, as well as a heuristic based on matching. Both these also involve the minimum spanning tree, which we would have covered by then under the network problems. There is a slight variation of the TSP, which is called the Chinese postman problem. In some sense, it is not a variation as such, it is a problem that is very close to the TSP. While the TSP talks about visiting every vertex or a node once and only once and coming back to the starting point, the Chinese postman problem talks about visiting each arc or edge of a network once and only once if possible, and coming back to the starting point. So, in that sense it is related to the TSP. We will see some aspects of the Chinese postman problem in this course, after which we will look at vehicle routing and distribution problems, which are typical extensions of the travelling salesman problem. In a vehicle routing problem, we talk about multiple vehicles originating from a point, picking up or dropping people or material or transport goods and come back to the starting point. So, a vehicle routing problem can be seen as multiple TSPs, and we also look at some more distribution problems where there could be a restriction on the size of the vehicles, there could be a restriction on the number of people that the vehicle could carry, and so on. So, we will look at algorithms to solve vehicle routing and distribution problems. After this, we will look at a bit of queuing theory, a bit of nonlinear programming, and a couple of additional topics. Queuing theory is perhaps the only topic in this course which is not deterministic in nature. Every other topic that we are going to see comes under deterministic OR, where the problem parameters are deterministic, known a priori. Queuing theory is perhaps the only topic in this course where we will look at some non-deterministic, some probabilistic models. So, here we will look at arrivals and service patterns, we will look at single server, multiple server systems, we will look at infinite queue length and finite queue length models, and so on. So, here we would assume that the arrivals will follow the Poisson distribution, the service times are exponentially distributed, and within this context we will see how the queuing systems are performing in terms of expected number of people in the system, expected number of people in the queue, the average or expected waiting time in the system, and expected waiting time in the queue. So, all these 4 parameters will be measured, and formulae or derivations to get expressions for these parameters will be shown and derived in this course. We will then look at nonlinear programming and nonlinear optimization. We would also look at the Kuhn-Tucker conditions, which are the conditions that are used extensively to solve nonlinear programming problems. We will also concentrate on one specific aspect of nonlinear programming, which is called quadratic programming, where the objective function is quadratic in nature, the constraints are linear, and there is an explicit non-negativity restriction on the variables. We will also show the algorithm to solve the quadratic programming problem, which involves linear programming principles. There are 2 other additional topics that we will look at. One is called CPM, which is the critical path method, and from an OR point of view, this can be looked upon as a network problem where we find the longest path of a certain type of a network. In general, the longest path on a network is a hard problem to solve, but certain types of networks which are there in the CPM, we will see that one can use a very efficient algorithm to find out the longest path. So, in some sense CPM can be seen as part of the network models topic, but CPM is a specialized application because of its use, extensive use in project management. We will also see some aspects of game theory, some simple things such as saddle point, graphical solution to a 2-person zero-sum game, and solution to 2-person zero-sum game using linear programming. In the earlier course on fundamentals of operations research, we have actually formulated the game theory problem as a linear programming problem. Now, here we will also show the primal dual relationship between A's game and B's game if A and B are the 2 persons who are actually playing this zero-sum game. So, this is in some sense the overview of this course and what we are going to see in the advanced operations research course. So, quickly coming back to the starting point of this course. So, we will now continue and begin this course formally by looking at the revised simplex algorithm. So, we start with the revised simplex algorithm. Now, as the name suggests, the revised simplex algorithm is a form of the simplex algorithm. So, before we get into the revised simplex algorithm, let us spend a little bit of time on trying to go through the basics of the simplex algorithm that we have seen in the earlier course. Now, in the earlier course we have seen that the simplex algorithm provides the optimal solution to linear programming problems. We have also seen that the optimum solution to a linear programming problem is a corner point solution, and therefore, the simplex algorithm is also tailored in that manner to find out the corner point optimal solution. So, the simplex algorithm starts with a corner point and then moves along the boundary of the feasible region from one corner point to another till it actually reaches the corner point, which is the optimum solution to the linear programming problem. Now, what does the simplex algorithm do? Now, if we consider a linear programming problem with n variables and m constraints, usually n is greater than m, the number of variables is greater than the number of constraints. We have already seen in the earlier course that these variables can be of several types. These variables can be the problem decision variables, they could also be slack variables, where a slack variable is introduced to convert an inequality into an equation, and within these slack variables it can be a positive slack or a negative slack. The negative slack is also called the surplus variable. It could also be artificial variables, where these artificial variables are introduced so that we are able to get an identity matrix in the simplex algorithm. So, the variables are of three types. The other way of saying that these variables from a simplex point of view can be a greater than or equal to variable, can be an equation, can also be a less than or equal to type variable. Linear programming problem also has constraints, and there are three types of constraints. The constraint is a greater than or equal to type constraint, it can be a less than or equal to type constraint, and it can be an equation. So, there are three types of variables in the linear programming problem, there are three types of constraints in the linear programming problem, and the linear programming problem also has an objective function which can be a maximization objective function or a minimization objective function. We have looked at three aspects of the simplex algorithm in the earlier course, and these three aspects are called initialization, iteration, and termination. Now, in the initialization, we try and bring the given linear programming problem into a format where simplex method can readily be used to solve. So, the initialization essentially tries to bring it into what is called the canonical form, wherein an identity matrix can be easily read from the starting solution. In the iteration, at the initialization stage, we assume that we have a basic feasible solution, and in the simplex algorithm This basic feasible solution is a corner point solution, and in the simplex algorithm we move from one basic feasible solution to another, from one corner point to another, and then at the end the algorithm terminates. In each iteration, simplex evaluates a different basic feasible solution. Now, what is this basic feasible solution? We have said that there are n variables and m constraints, and let us assume that these n variables include all the types of variables, which means all the constraints have now been converted to equations, and if required all the artificial variables have been added, so that n is clearly greater than m. Now, once we have more variables than constraints, we also know that if we want to solve equations, we can solve only for as many variables as the number of constraints that we have. So, we can solve only for m variables in any iteration. So, out of these n variables that we have, n is greater than m, we choose m variables to solve, and the remaining n minus m variables will be called non-basic variables, which are fixed at 0, so that we solve for the rest of the variables which are the basic variables. Such a solution is called a basic feasible solution, and this basic feasible solution will be a corner point solution. So, in the initialization we ensure that we get a basic feasible solution. In iteration we move from one corner point solution to another with progressively better values of the objective function. If the problem is a maximization problem, we also ensure, we not only ensure that every basic feasible, every solution evaluated is basic feasible, we also ensure that the objective function does not decrease or increases in every iteration. At the end, the algorithm will terminate either when it reaches the optimal solution or some other things happen. So, now to understand the termination condition, we should also go back and review the fundamental theorem of linear programming, which says that every linear programming is either feasible or unbounded or infeasible. So, every linear programming is either feasible or unbounded or infeasible. Now, the fundamental theorem also says that if it is feasible, it has a basic feasible solution, and in this case it is expected to terminate with the optimum solution. So, simplex will terminate either with the optimum solution or by indicating an unbounded solution or by indicating an infeasible solution. Now, within this optimum case, you will have a unique optimum or you will have an alternate optimum. In the unbounded, we need to we have defined the termination condition for unbounded, and we have defined the termination condition for infeasible in the earlier course. Let us quickly take stock of that. Now, in the format that we have used, we will find that all the Cj for a maximization problem, all Cj minus Zj is less than or equal to 0, we say that the optimum is reached. Once the optimum is reached, if we have another non-basic variable with 0, then it indicates alternate optimum. These are the two cases, unique optimum and alternate optimum in this case. If we have an entering variable, which means if we have a variable with a positive Cj minus Zj, it can enter, and we are unable to find a leaving variable, then it indicates unboundedness, and the linear programming problem is unbounded. And in the infeasible case, there is one way of showing infeasibility, that the optimality condition is satisfied, which means all Cj minus Zj is less than or equal to 0. However, you still have an artificial variable lying in the basis with a strictly positive value. If that happens, then we say it is infeasible. Now, if all Cj minus Zj is less than or equal to 0, and if we find an artificial variable with the value equal to 0, then we may say that the system of equations is linearly dependent. So, simplex has its own way of showing even that the system of equations is linearly dependent, and therefore, simplex can be used to solve a system of equations. But coming back to the point that we are discussing, the three aspects are feasible, unbounded and infeasible, and these three define the termination condition for the simplex algorithm. In addition, we may say that if simplex does not terminate in spite of all these, then simplex does what is called cycling, simplex cycles. We briefly mentioned about cycling in the earlier course. Cycling is when you start with a set of basic variables which is called a basis, and after several iterations you come back to the same basis. Now, such a thing is called cycling, and there have been some instances where simplex had actually cycled. Cycling is a limitation of the simplex algorithm, and it has nothing to do with the linear programming problem. People over the period of time have also found out ways by which cycling can be eliminated. Cycling can be eliminated by the use of what is called the lexicographic rule, and it can also be eliminated by the use of what is called the Bland's rule or the smallest subscript rule. So, if there is a tie for a leaving variable and if there is a tie for the entering variable, we will always choose consistently the variable that has the smallest subscript, and that is enough to prevent cycling. There is a proof that the smallest subscript rule is indeed optimal. The lexicographic rule involves a little more computation, and we would look at the lexicographically smallest variable to be the choice for the leaving variable or the entering variable if there is a tie. So, either of these rules can be used to prevent the cycling of the simplex algorithm if it really cycles. Incidentally, we still have not come across any problem that has been formulated out of a real life situation which actually cycled. Most problems that are available in the literature which cycle are problems that have been created by the researchers themselves. Now, having seen so much of linear programming problem and the simplex algorithm, we will come back to where we wish to start, which is to look at the revised simplex algorithm. Now, what is this revised simplex algorithm, and why do we need the revised simplex algorithm? Before we get into that, let us look at two aspects of the speed or goodness of the simplex. The two aspects are time taken by the simplex algorithm per iteration, and two, the number of iterations. So, we have to look, if we want the simplex algorithm to be a very fast algorithm, then simplex has to be good on these two dimensions. The time it takes per iteration has to be as small as possible, and the number of iterations it takes before it terminates should be as small as possible, so that simplex algorithm is able to give the optimal solution very quickly. Now, let us see what actually happens in these two aspects of the simplex algorithm, and then move on to go to this revised simplex, which essentially tries to minimize the first one. Of course, there are some advantages of the revised simplex algorithm as well. So, we will first look at the number of iterations, and then we will look at the time per iteration, and then proceed towards the revised simplex algorithm. Now, let me show the simplex table first and then address the number of iterations aspect. Now, if we take a 4 variable 2 constraint linear programming problem and call our variables as x1, x2, x3, x4, then in the simplex table convention that we have used earlier, now this portion has the basic variables. So, let us call x3 and x4 as the basic variables. Now, we have something called CB, which is the objective function coefficient of the basic variable. So, you will have C3 and C4 here, and in the simplex table, because x3 and x4 are the basic variables, you will find an identity matrix under these, and then you will also find some coefficients which are here, which we may call as some A11, A12, A21 and A22. We call here the objective function coefficients to be C1 and C2. If we assume that x3 and x4 are the slack variables, you would start with 0 0, which means C3 is 0 and C4 is also 0. Then we evaluate Cj minus Zj, which is this minus the dot product of these two vectors. So, in this case it will be simply C1 and C2, because these are 0. So, you will have 0 0, and this will be the right hand side value, which would be some B1 B2, and this will be 0, because the right hand side will be the product sum of 0 plus into B1 plus 0 into B2, which will be 0. Now, if this is the optimal, or this will be the optimal solution if C1 and C2 are less than or equal to 0. If one of them is positive or both of them are positive, then the one variable will enter the basis. Now, that is called the entering variable, and then once a variable enters, there is something called the leaving variable. For example, let us assume that C1 is positive, and for a moment C1 is greater than C2. So, C1 will enter based on what is called the largest coefficient rule. That variable, if more than one non-basic variable, in this case x3 and x4 are basic, so x1 and x2 are non-basic. If more than one non-basic variable has a positive Cj minus Zj, then the one that has the most positive value will enter based on what is called the largest coefficient rule. So, let us assume that C1 is greater than C2 and both are greater than or equal to, or both are greater than 0. Therefore, C1 will enter based on the largest coefficient rule. Now, this is called the entering variable. Now, we need to find out a leaving variable. To do that, we compute something called theta, which is B1 by this, B2 by this, provided this coefficient is strictly positive. In simplex, right hand sides are always greater than or equal to 0. Therefore, the theta value has to be strictly positive. So, if this one is theta value can be 0 or strictly positive, theta cannot be negative, because when these become 0 or negative, we do not evaluate the corresponding theta. We have already seen that theta represents the extent to which this variable can be increased or this variable can go up till this current basic variable becomes 0. So, let us assume that all these are non-negative, they are non-zero, they are strictly positive. So, we will evaluate B1 by A11 and B2 by A21 and choose the minimum of them. So, the minimum will leave. For example, if this is smaller, then this will leave. This is called the leaving variable. When there is a tie for the leaving variable, we say that there is degeneracy and there will be a 0 in the next iteration. There is also a choice for the leaving variable. At the moment, we do not have a very specific tie breaking rule for the leaving variable, but in order to safeguard ourselves against cycling, it is always good to consistently use the smallest subscript rule to identify the leaving variable if there is a tie. Now, the real issue comes in deciding the entering variable. Now, if we said that if more than one is positive, we could enter with the most positive one. For example, if this is 8 and this is 8, if this is 8 and this is 6, then this is 8 and this is 6. Now, based on the largest coefficient rule, this one will enter. There is nothing wrong in actually entering this as long as this is positive, but by convention we always use the largest coefficient rule. Now, the question is, by a judicious choice of the entering variable, can we bring down the number of iterations in simplex, or can we reduce the CPU time or the computational time required for simplex? So, people started working on what are the various ways by which you can enter a variable if you have more than one variable with a positive Cj minus Zj. There are 4 very popular rules that are being used for the entering variable, and these 4 famous rules are the largest coefficient rule, the largest increase rule, first positive rule, first positive coefficient rule, and random positive coefficient rule. We have already seen the largest positive coefficient rule. If you have 8 and 6 here, both are positive, so any one of them can enter. This has a larger coefficient, so this enters. So, by the largest coefficient rule or the largest Cj minus Zj rule, this will enter. Now, what happens if it is the largest increase rule? Now, what we will have to do in the largest increase rule is, let us assume that these values are 1 and 3, 2 and 2. Let us assume this value is 10 and 6. Let us assume this is 1. So, this has a positive value. So, if we enter this, then the leaving variable is 10 divided by 1, which is 10, 6 divided by 2, which is 3. So, the minimum of that will be 3. So, theta will be 3. Now, in the next iteration, the increase is always the product of Cj minus Zj and the corresponding theta. So, if we enter this, Cj minus Zj is 8, theta is 3. So, the product is 24. If on the other hand we choose to enter this, now the corresponding theta will be 10 divided by 3, 6. So, 10 by 3 will be theta. So, this will be 6 into 10 by 3, which is 20, and therefore, once again this will enter based on the largest increase rule. But if on the other hand this also had been 1 and if this enters, now theta will be the minimum of 10 by 1 and 6 by 6, which is 6. So, the increase will be the product of Cj minus Zj into theta, which will become, here you will have 10 and 6, this is the minimum theta. So, 6 into 6, 36. If you had entered this, it will be 8 and 3, 24. So, based on the largest increase rule, this variable will enter, because this shows a larger increase from 0 to 36, whereas this would have increased from 0 to 24. So, depending on the rule, a different variable will enter. and the basis can change. The first positive Cj minus Zj is a very simple rule. Simply look at the Cj minus Zj row and identify the first positive Cj minus Zj. In this case, this will enter because this is the first positive Cj minus Zj. If for a different problem, the Cj minus Zj values are -3, 1, 9, 0 and 0, this will enter because this is the first positive Cj minus Zj. Random positive Cj minus Zj is there are 5 values, randomly pick one, if it is positive, enter. So, if the random number chosen is 3, then this will go. If the random number chosen is 1, it will look at this -3 and say that this is not positive, therefore choose another random number, and if the random number becomes 2, then it will look at the second position, there is a 1, so the second variable will enter. So, like this we can start defining various entering rules, so that the simplex algorithm proceeds by identifying a newer solution. Now, let us try and look at all 4 of them. Now, this is the simplest and the easiest. From a computational viewpoint, we need this vector, the Cj minus Zj row, and in some sense we have to identify the largest, which means it is equivalent to sorting it based on decreasing value and picking the first. So, the computational effort involved is simply sorting a given vector. Now, here for every positive you have to find out a theta and then multiply and then find out that variable which has a positive Cj minus Zj and has the highest increase. So, this requires a little more computation than this. These two also require lesser computation. Here it is much simpler, you simply look at the vector and find out the first positive value and enter that variable. Here there is a certain computation involved because you have to randomly start picking a variable, check first of all whether it is positive, if so enter, if not randomly pick another variable and so on. So, out of all these 4, based on computational studies, people found out that this requires fewer iterations, this requires fewer iterations in general, but this takes the least CPU time compared to all 4 of them. So, in terms of computational time, people said this is a good rule, this is the best out of these 4 rules. And based on this, simply because we want our simplex to be quick, we always try and pick the largest coefficient rule, even though for other problem instances we may have a situation where other rules can do better. So, we pick the largest coefficient rule usually in solving using the simplex algorithm, simply because computational tests have shown that it takes the least amount of CPU time or least amount of computational time. So, it is always possible, or it is always this always happens that we end up choosing the one which has the largest coefficient or the largest Cj minus Zj. The leaving variable rule is always the one with minimum theta, and if there is a tie, it is always good to choose the minimum subscript consistently, so that we safeguard ourselves against cycling in linear programming. So, we try to answer the first question, which is what is the entering variable, or how is the entering variable chosen. So, entering variable is chosen based on the largest coefficient rule. Let us go back to the 2 questions that we asked when we began, which are the number of iterations and time taken per iteration. So, in some sense we solved the number of iterations problem by looking at the largest coefficient rule. One may argue that the largest increased rule actually has fewer iterations, but then it is not only the number of iterations, it is the total CPU time. And because we want the total CPU time to be minimized, we prefer the largest coefficient rule in preference to the largest increase rule. So, we move to the next one, which is time taken per iteration. Now, what is the time taken per iteration? Let us assume that we have an iteration like this, from which we are going to move to another iteration. Now, let us assume that this is the entering variable, and based on these numbers, this is the leaving variable. Because the moment this is the entering variable, you need to compute the theta. 10 divided by 1 is 10, 6 divided by 2 is 3, the minimum theta leaves. So, this is the one. This is called the pivot row and this is called the pivot element. Normally, in our tabular form or hand calculation of simplex, we follow a set of rules which are divide every element. Now, we replace this. So, x 3 remains, x 4 is replaced by x 1. Now, when we had x 3 and x 4 as the basic variables, you had the identity column somewhere here. Now, in this iteration, we will have to ensure that the identity column shifts to x 3 and x 1, so that the solution whatever we get here is the corresponding basic feasible solution. So, we need to do row and column operations such that we retain the 1 0 here on x 3 and we have 0 1 on x 1. So, the identity matrix taken as x 3 x 1 will have 1 0 here and 0 1 here. Now, we achieve this in the tabular form using a certain set of steps, which is divide every element of the pivot row by the pivot element, which would give us 2 divided by 2 is 1, 1 divided by 2 is half, 0, half and 3. Now, to fill the rest of them, what we have to do is this. I need a 0 here. So, this minus this is 0. So, 1 minus 1 is 0, 1 minus half is half, 1 minus 0 is 1, 0 minus half is minus half, 10 minus 3 is 7. So, through these two steps, the pivot row is always divided by the pivot element. Rest of the rows you do row operations such that you get the identity matrix on this. You will automatically retain the identity matrix on this and you get the next iteration. Now, this what we have done here is the famous Gauss-Jordan way of solving equations. It is called the Gauss-Jordan method of either solving an equation or inverting a matrix. We have already seen in the earlier course that if x 3 and x 1 are the basic variables, we can go back and find out the basis matrix and you can invert it, you will get exactly this. Now, this is true because what we have actually done is, if x 1 and x 3, if x 3 and x 1 are your basis, so you start with 1 0 1 2. Now, we have got 1 0 0 1, which means you have pre-multiplied it by its inverse. So, you have pre-multiplied it by a B inverse to get 1 0 0 1. Now, this is an identity matrix. So, you pre-multiply it by the same B inverse to get 1 0 and minus half half. Therefore, under the original identity matrix, you will have the B inverse. We have also seen that every iteration of simplex is equivalent to solving equations. Now, this is equivalent of solving for something into x 1 plus something into x 3 is equal to 1. This is equivalent of solving some other thing into x 3 plus some other thing into x 1 is equal to 1. So, every iteration of the simplex is about solving set of equations. It is about solving for the basic variables, and in the hand computation that we have seen, we do it using the Gauss-Jordan method, and we also know that solving for equations is the same as inverting a matrix. And we have effectively used the Gauss-Jordan method to do that. Now, the next question is, what is the computational effort that is required in these iterations? Now, if we see these iterations, if we really follow the simplex, what we actually require is, if these two are the basic variables, first and foremost we want the values of C j minus Z j corresponding to these basic variables. We really do not need to compute all this. All we need is to compute the C j minus Z j of the non-basic variables, which are x 2 and x 4. We just need these two values, because we already know that C j minus Z j for the basic variables will be 0. So, if these two values we need to compute, if these two values are less than or equal to 0, then we have reached the optimal solution. So, we just need to compute these values first, and when we compute these two values, we will know whether the present solution is optimal or some other thing is required, or one more iteration is required. Now, once we know that another iteration is required, then you need to find out which of these variables enters and which of these variables leaves. So, in order to find the entering variable, then we require, let us assume that between these two this variable enters. So, this variable enters, then we require this column, we require this column, so that the leaving variable can be found out and the next one can go. If it is optimal, then we require only this, so that we can find out the solution and also find out the value of the objective function. So, in some sense what we require first are the C j minus Z j values. We require this value. Now, here we have n minus m values, because there are n variables, out of which m variables are basic variables which will have 0. So, the remaining n minus m variables will only have values which are non-zero, and it is enough to find out this n minus m values. Once we know that there is an entering variable, we need to find out this column, which is another m values. We need to find out this column, which is another m values, and then we need to find out the leaving variable, which is a simple division, and then proceed. But in order to find out this value and this value, we have already seen in the earlier course that this is given by the expression p bar j is B inverse P j, and it is also given x b equal to B inverse B. Now, what are these P j and B? P j is the corresponding value in the first iteration, B is the corresponding right hand side values which are known. Now, what is required further is this B inverse, and we have already seen in the earlier course that B inverse appears under the original identity matrix, which means we also require this, which also means we require another m into m. So, every iteration actually requires m square plus m plus n computations, plus 1 if you need it, plus 1. That many computations are enough, but what we end up doing is we actually evaluate completely all this, which is effectively m plus 1 into n plus 1. So, can we have an efficient algorithm which will evaluate fewer numbers than evaluating this entire rectangle, which is m plus 1 into n plus 1. So, that is the first thing. If we wish to make simplex better in terms of the number of computations and in terms of the memory and storage, particularly storage required for the simplex. We also realize that out of these, computation of B inverse is the most intensive or intense computation, while the rest of them are only matrix multiplications. So, a large amount of effort in the simplex iteration actually goes in finding out the B inverse. So, there is a basis matrix associated with every iteration, and a large amount of computational effort goes in trying to find out the B inverse. Now, in this method we actually find out B inverse using the Gauss-Jordan method. So, the focus shifts on trying to find out the best way to invert a matrix if you really want to solve a simplex iteration quickly. So, the speed of the simplex algorithm depends on the time it takes to invert a matrix. So, the emphasis shifts from performing these iterations to saying how quickly can I invert this matrix. So, there are two issues in making the simplex faster. One is to find out an efficient way of matrix inversion, and the second is to make minimum computation that is required and not more than the minimum computation that is required. So, we will look at both these aspects of how well we can invert this matrix and how do we develop a method by which minimum computation is required by taking a numerical example.